So the second set of demos deals with the concept of central points, which we already touched upon last week, and the concept of tessellations. Anybody familiar with what a tessellation is? The word Thiessen polygons ring a bell? Delaunay triangulation, it's all the same thing, okay? Tessellation is a division of an area by regular units, and you'll see in a few minutes what I mean. So let's first go back to our central points. And if you saved this last time, you will still have it, but I didn't save it. So I go on the map in the menu, and you remember shape centers. And I'm going to save the mean centers first. And just like last week, what am I doing here? Add mean centers to table, sorry. First one, right. So add mean centers to table. We take coordinate X, coordinate Y, right? Just because it's easy. And now we're going to also add shape centers, add centroids to table. And we're going to give them a different name. We don't want to give them the same name. For example, CX and CY. Okay. So it's the same thing both time. Add shape center to table, either mean centers or centroids. What's the difference between the two? No clue? Exactly. So one is a weighted center, the other one is an unweighted center. So the mean centers is simply the mean of the X's and the mean of the Y's. The centroid is a weighted center, weighted by area. The centroid, if you can think about it, if you cut out, think of a cardboard area, you cut it out, and you find the point in the middle where you could put a pin, and the cutout is in perfect stable equilibrium. That's the centroid. So in a sense, it's a weighted average, weighted by area. The simple average, there's no area, doesn't matter, just X and Y. But with the centroid is a weighted area. Does this matter? Yes and no. I mean, when the areas are nice and compact, they're basically the same. When they're weird, like O'Hare, they can be quite different. Okay. So to show you this, I have the map here. And I'm going to go back to the same menu, but now instead of saving them to the table, I'm going to display them. So the first set is the mean centers. You see the little dots? And if you remember from last week, some of them are nice in the center, like this one, and some of them are in weird spots, like this one was on the edge of the border, right? And now I'm going to do the same thing, shape centers, display centroids, and there's a second set of points. And in some areas, like here, like here, you can barely tell them apart, right? They're just shifted a little bit. But in other areas, they're actually quite far apart. Again, if we go to O'Hare, look at these. There's some other ones where they're quite far apart. And that really depends on the shape of the area. So in practice, it doesn't matter that much, because what we're going to do is simplify the aerial units to points by a representative point. The mean or the centroid are pretty representative of the shape of the area, but essentially we do this when we want to focus on distance rather than borders and the actual layout of the polygon. So we simplify the polygon to a point, but in GeoDa, it's still the exact same data set. So the data, the attributes don't change, the spatial representation changes. So it's a different spatial representation of the same thing. And just to illustrate this, we're going to use the tools, the little hammer here, and we're going to tools, points from table. What we're going to do is create a new layer, a point layer. Remember last week what we did, we saved the file as CSV, and then we pulled in the CSV and turned it into a point layer. Now we're going to do this, and you can do this with any two coordinates that you want to be X and Y. So typically these are real coordinates, but they don't have to be. So you can create things that are maps for things in kind of multivariate space, because there's no borders, it's just points. So if we take this points from table, and let's say, just like last week, we take coordinate X for the X dimension and coordinate Y for the Y dimension. And then it's going to ask me, where do you want to save this? And I'm going to want to save this to my, as a shapefile, to my lab directory. And I actually have them already. Let me call it, oops, not this one. Chicago, you can call it anything you want. And it already exists, don't worry about it. I mean, it probably won't exist for you, but, and see this here, what does this tell you? The CRS, remember, coordinate reference system. What does this one tell you?
Decimal degrees.
Decimal degrees, yeah. So it isn't actually a projection. It's just decimal degrees. But for our purposes, we don't worry about it. Later, when we need to calculate distances, we are going to worry about it. Okay, because when you have decimal degrees, you have to compute an arc distance on a sphere. When you have projected Cartesian coordinates, a straight line distance. Yeah. So we're in business, we have it, okay? Now I'm going to close, and I don't think I need to save my data, so I'm not going to save it. You should save your data to your working directory. I mean, you don't have to, but it's easier. So now I'm going to open, and I need to pull it from my directory. So I open my lab directory, and I'm looking here, where are the, here's the Chicago points file, and I'm going to drop it, pull it, and drop it, come on, here. And what's going to happen, I'm going to have my green base map. But the green base map only has points. Just like last week, when we took the CSV file, we just have the points. Right? And keep in mind, this is only a different spatial representation of the same data. The data have not changed. Okay, so it's the same table. We can do the same statistical analysis. The only difference is that the representation is now in terms of points and not in terms of polygons. Okay. Now the tessellations. Tessellations are a way of divvying up space. And so what we're going to do is create something which is the equivalent of in economic geography, what is called a market area. So think there is a very famous problem. It's called the hoteling problem. When we talk about location, we'll probably talk about that. Is the location of hot dog vendors or ice cream vendors on a beach. So think of the beach as a linear space. Everybody can walk everywhere equally easily. People on the beach are spread uniformly. So, no grouping, everybody is so many feet apart and they're on the beach, okay? If you're a hot dog vendor, where should you locate? There's 2 hot dog vendors. Where should you locate your stand to maximize your profit? So profit is very simple, is how do you reach the most people, the closest to you? So this becomes spatial. There's no rich people or poor people, they're all the same. They're all just laying on the beach. They want ice cream. The only thing they don't want to do is walk very far. But you don't care about that. You want to sell ice cream. So where do you put yourself to sell the most ice cream? Any idea? In the middle of the beach. So that is a famous, it's actually underlies also game theory. It's a famous problem. And so you go back to back. That is why when you start paying attention to these things, why are car dealerships all together? In fact, in some places, they now become locations at the outskirts of the city where every car dealer is just next to each other. And they're competitors. They're not the same company. Why do they do this? Because it's easier for people to go to the same spot rather than for one brand you go there, for the other brand you go there. So they actually, even though they're competitors, by grouping together in space, they actually maximize their profits. So these are the kinds of things. Now, why do I say all that? Because when you look at Thiessen polygons, okay, first we're going to display them. So it's again on the map menu, you go to Thiessen polygons, display Thiessen polygons. There they are. And these divvy up the space so that any location within the Thiessen polygon is closer to the central point than to any other point. So all these points here are closer to this point than to that point or to that point. In fact, the way the Thiessen polygon is constructed is you connect these 2 points and then you take the midline perpendicular to it. And there's several algorithms to do this efficiently. But if you look carefully at each of these points, if you look at 2 adjoining points, the line is perpendicular to the line that connects the 2 and separates the areas into multiple polygons. So why is this useful? Because this is yet another way of representing space for the same data. And especially later on, when we deal with the concept of spatial autocorrelation, we will have to define neighbors. And if you just have the points, how do you define the neighbors? You can say, well, if they're within a given distance, or if they're the nearest neighbors. But there's another way to define this by being neighbors, having a joint boundary in the Thiessen polygon space. So that's yet another concept of neighbors. And here again, we can save this, save the Thiessen polygons, same routine. You set the file name, for example, Chicago TH. Again, it's going to give me a warning. You won't get this. It's okay. Same CRS. Okay. Okay. And now we close. We open. We find this Chicago Thiessen here. And I pull it in. And here's our polygon. So we have three different representations: the original aerial outlines, their simplification by a central point, either the mean center or the centroid, and then an abstraction where they become abstract areas. And just like before, we can add mean center to the picture, and then you see the same thing again as before. Okay. So this is what you can do with the tools. You can do other things with the tools. We'll talk about that later. But here, the tool menu, we can create points from table. And then in here, we can create Thiessen polygons. Here, it doesn't work because they're already Thiessen polygons. Okay. So that's a new concept. We have a concept of mean center. We have the concept of centroid. We have the concept of a tessellation. A Thiessen polygon is a particular example of a tessellation. The Delaunay triangles are triangles that connect these points, basically the points that are adjoining in the Thiessen polygon. So the Delaunay triangle, you may see this in some of the readings later, is what is called the dual of the Thiessen polygons. So it's the same thing, but the opposite side of the coin, so to speak. So you either represent it as these polygons, or the same network structure can be represented by the triangles. It's all the same thing. We use the term Thiessen polygons.